Hey, I'm glad that you're willing to come into this journey with me. Hopefully, it's the first step to many, and hopefully, this ride doesn't turn out to be bumpy. So, eventually, in the future, I want to be able to talk to you guys as if I was talking to a math major, and maybe in the future, we can communicate like as if it was math major to math major. That being said, I'm gonna introduce to you guys to a bunch of ideas that you probably never seen before. And that's what I mean that hopefully this journey isn't too bumpy. I mean, in my intro video, I told you guys that we're gonna start mathematics from the ground up, from the beginning, right? So, if we're gonna try to attempt to talk about where mathematics should begin, um, we might be talking about some crazy things. So, where do you think math should begin? I mean, take your best guess, right? Put it down in the comments or whatever. Um, let's see if you guess right. Where I think, so this is just my opinion. Where I think we should start is actually with sets. Yeah, sets. I don't know if you heard that right. Now, don't leave. Don't leave. I promise you, this is mathematics. This is math. We're gonna talk about math. You might think, why sets? Why should math start with sets? Well, the reason why I think math should start with sets is because sets is where mathematics happens. You know, the topics of mathematics deals with what numbers, functions, graphs, geometry. Well, what people debate, what's mathematics? Is it all in your mind? Is it a real thing? Well, the mathematic process definitely happens in the mind, right? But we can actually ground, where in the mind per se this happens. So, like I said, I'm claiming that mathematics happens in sets. So, what is a set, right? Sets. S-E-T-S. So, let's define a set, more or less, right? A set X, capital X, is a collection of definable objects. If, let's say, little a is an element, is an object of X, the set X, we say A is an element of X. And so mathematicians have their own very alien language, which I'll teach you guys. Well, I'll show it to you guys as it comes up, right? So in this case, we say that A belongs in X this following way. A, this symbol, and X. So this little thing says A is an element of X, A belongs in X, however you want to read it. Now, a few things. Well, first of all, I'm going to use capital letters usually to denote sets, and I'm going to use lowercase letters like little a to indicate elements. Now, the reason why we call them elements is because, mathematicians don't just look at numbers, we look at a lot of things. So, if we just say that if we only say that sets have numbers, then we would be really limiting our scope, right? Now, again, I'll try to use lowercase a for elements and capital letters for sets, but actually, sets can be made up of sets. Again, we use the word element because the things inside the sets could be anything. So it wouldn't be we wouldn't put it past that some sets are made up of sets. Another thing I want to say is definable, right? Definable objects. What does that mean? I mean, it doesn't sound like a concrete definition, right? Well, when people say definable objects, they they just don't want you to come up with a set that's gonna cause problems, some type of paradox. Well, so for example, right? Let me just give you an example of something that is a set, right? If I say that this set is equal to just the numbers 1, 2, 3, right? So again, it's a collection of objects. The objects in this case, yeah, they're numbers 1, 2, and 3. What makes it definable is that I actually explicitly wrote down what the elements are. You know, I defined that the only elements in the set A are the number 1, the number 2, and the number 3, right? Let me give another example. Let's say a B is now, let's say, even positive numbers, right? Now, so I'm saying that the set B is just contained of even positive numbers. Well, so for example, I'm saying that 2 belongs in B, right? Because 2 is positive, it's even. Well, that's all you need, right? All you need to be is even and positive to be here, right? So at this point, you can conclude that B. You can also try to list it out, but the difference between A and B is that now you have an infinite set, right? B contains 2, 4, 6, 8, 10, 12. Well, actually, it contains an infinite number of elements, and usually when a set does that, we just put 3 dots. We kind of show like some type of numbers with a certain pattern, and then we put 3 dots to indicate, well, you kind of get the pattern, right? So again, so far, yeah, if you write it as B equals even positive numbers, that's definable enough. You know, there's no ambiguity of what the elements are here, right? So then now maybe I should show you what isn't a set, right? Well, there are 2 standout paradoxes basically that we try to avoid. Again, you might think you can make a set out of anything, right? As long as it's definable. Well, you can say let U be the set of all sets. Okay, it sounds reasonable enough, right? But you know, if U is the set of all sets, at this point you think, well, U itself is a set, right? So then you have that U belongs in U, right? I mean, I put a question mark, but again, right? If U is the set of all sets, this thing is itself a set, then U should belong in itself. Well, this particular set, if you want to call it that, later on brings a big a big problem. So people just mathematicians just agreed, okay, actually this is not going to be a set. In fact, they end up agreeing that no set can contain itself. Again, if you're wondering, well, what's the problem, right? There's a thing in the future that's going to be called the power set of a set. So the power set of some random set equals all subsets of whatever it is that set that you're looking at. So the power set of a set A will be all the subsets of A. What's a subset? We'll get to it, right? But again, this particular set brings a whole set of problems when you look at the power set of a set. All right. Again, the conclusion is that anytime a set contains itself, we don't like that. At least in the current, in the established axioms of set theory, right? So just again, the takeaway right now is a set. We don't want a set to contain itself, right? Another paradox is by Bertrand Russell, a famous philosopher, right? Probably heard him, even if you don't like math. But he has a paradox about a barber who says there's a town where everyone must be shaved, no facial hair, I guess, right? And then there's only one barber in the town, and for some reason they task this barber with the duty of having to shave facial hair of people that can shave themselves. They say, okay, you can only shave people who cannot shave themselves, right? So yeah, if you can shave yourself, that's fine. If you cannot shave yourself, you go to the barber. And then the question happens, well, what about the barber himself? If the barber shaves himself, he is no longer shaving people who cannot shave themselves, right? But then if he can't shave themselves, who's gonna shave him? So again, there's a lot of YouTube videos that you can look up if you wanna just look up Bertrand Russell barber paradox, right? But in set theory, they put it this way. Suppose you have a set of sets, but in particular you're saying, oh, I'm looking at all the sets where the sets don't contain themselves, right? So the set B is equal to all sets that don't contain themselves. Well, then the question now arises, does B contain B? Right? Well, again, maybe we need to establish a couple things, but if it's true that B contains itself, right? How could it be that if B is in B, then by pure definition, then if B is in B, then it has to be also true that B is not in B. On the other hand, the opposite of it is that suppose that B is not in B. Well, if B is a set that's not in B, then it's a set that's not in itself. Then that turns it back into then B is in B, right? So again, if B does contain itself, then B belongs in this set. But you can only belong in the set if you satisfy that you don't belong yourself, right? So if B belongs there, then it doesn't belong there. Okay, then if you assume, however, that B is not there, by the pure definition of this set, then you are there. So again, now that's a paradox, right? Okay, so again, these are two examples of sets that aren't sets because they break. For now, let's just say that they break the definable part. Okay. Well, like I said, let me expand a little more. So in general, when you create a set, right? A very standard procedure is to say, okay, the elements satisfy something, So, for example, I'm going to define my set C. Well, how do you define things? Well, first you kind of specify, the elements sometimes. Sometimes you say, my elements they look a certain way. But then you add to that and you say, well, they don't just look a certain way, but then they also satisfy a statement, Um, so in mathematics, sometimes we say that P is a statement, and we say P of C is true. So again, let me give you an example, right? I can make up a set. So the set of let's say real numbers such that well, let me do it again. Let me define C as the set of numbers, so I'm just going to leave it as X, such that these numbers satisfy just anything. So for example, so I guess what I'm trying to say is that this is very standard to do. Sometimes you say, yeah, a set is going to be some type of element that makes some type of statement true. Again, as an example is, I'm just saying X is so that X squared equals 4. Usually though, I would say it's kind of sometimes important to clarify more on this side. So for example, you could very well say that, well, actually this set only has two numbers. This set has 2 and -2, right? Now if you come up with a different set, like X such that X squared plus 1 is 0, well, actually for this specific statement, depending on how you specify here what it is, then you could have different outcomes. So for example, if I say that, if I explicitly say that X is what we're gonna call real number, if I specify that X is a real number, then at this point actually there is no element that does that. There are no real numbers such that X squared plus 1 equals 0. So now, surprisingly enough, this is not a paradox. We're just saying that there are no elements that satisfy this statement. So we basically have a set that has no elements. Whenever we have a set that has no elements, we call that the empty set. So this symbol right here is the empty set, which is just this set has no elements. However, if there's a way so that if X is something else, then now D wouldn't be empty anymore. Wow, I didn't think I was gonna take so long to just say what I've said so far. Well, again, maybe I dropped a lot of things onto you, and actually there's a lot more to get into sets. There's a lot more to get into, but again, why did I choose sets to be the beginning? Well, I mean, I think if you don't know anything about sets, you might agree that maybe, well, math, no matter what type of math you do, you deal with numbers, and no matter what you're doing, what numbers you're looking at, numbers start with the number 1. So you could say that the number 1 itself, as an idea, is where mathematics begins, right? Well, yeah, I guess I would agree so too, right? So I guess a big reason why, like I said, I do stand by what I said, that all of mathematics happens in sets, right? Well, I mean, yeah, the first, if mathematics happens in sets, the first set to look at is this one, n for natural numbers. So the set that contains basically 1, but then if 1 exists, then 2 is going to exist. 1 plus 1 is 2. But if 2 exists, 1 plus 2 is 3. If 3 exists, 1 plus 3 is 4. So on and so forth, right? So again, you see a pattern, hopefully, right? So I'm just going to put ... close the bracket. So I would say, yeah, I mean, math, I guess, starts with the natural numbers. Now, this might be a little controversial, because I think in some places people have the 0 as part of the natural numbers, but I'm going to keep it this way only because the natural numbers are also known. So natural numbers, but they're also known as the counting numbers. I mean, it makes sense, right? I mean, if you think about numbers, where did numbers start? It must have been someone, maybe like a farmer that had a bunch of sheep, and the farmer knew that he had a bunch of sheep, but he didn't know exactly how to quantify. So how would you solve that problem? You just start counting them, right, with your fingers. Maybe have 1 sheep, 2 sheep, 3 sheep, 4 sheep. So again, that's why I'm not going to include 0 for this set, because no one starts counting at 0, 1, 2, 3. Maybe some people do, right? But yeah, so as soon as you have 1, you really have all these numbers, right? Because I mean, 2 is just 1 twice, 3 is just 3 once, 4 is 4 once, 5 once, so on and so forth, right? Now, historically, right, what do you do with numbers, right? Well, you add them. That's how you get more numbers. But if we're also talking about counting goes hand in hand with multiplying, right? So you multiply numbers as well. But if you add, sometimes you want to undo that process, so you subtract. And if you multiply, sometimes you want to undo that process and you divide, right? So historically speaking, I would say that fractions are probably the numbers that came after this ones, right? However, the next that I want you to show you is the integers. So the integers, like I said, I know historically, fractions probably come out first, but again, right? I'm sure before you start multiplying, you start adding. And one thing that comes with adding is subtracting, because if you have $10 and you pay something that cost $5, right? How much do you have left? Well, you have to subtract. Well, what if you owe somebody $10 and you only have $3, right? Now 3 minus 10 is -7. Some of you guys might know that. But negative dollars isn't a real thing, right? What it means is that if you have $3, you owe 10. Maybe the person comes collect, they take you $3 and they tell you, well, by the way, even though you have $0, you still owe $7, right? So that maybe that's where -7 comes from. Just the idea of owing. Anyway, so that's what I'm trying to say. After the natural numbers, I think the next important set of numbers is to talk about is the integers, which is just basically, I mean, I want to say whole numbers, but I think some people refer to whole numbers as something in particular. But yeah, like things that don't have decimals, right? So still 1, 2, 3, 4, 5, but also -1, -2. We have -7, negative everything, right? And then also 0, right? Okay, but where do we go next? Like I said, with adding comes subtracting, when multiplying comes dividing, right? So then the next important set of numbers that we're always gonna be interested in are these rational numbers. So not necessarily exactly a fraction. A rational number is any number that looks this way: a over b, so long as. So yeah, maybe I should have explained that. Every time I write a line here, it just means such that. Some people do 2 dots instead. So a rational number is going to be any number that looks like a over b, so long as a and b are integers, and the one exception, b cannot be allowed to be 0. So for example, I want to point this out really quickly, right? So for example, 1/2 is of course a rational number, but it turns out, as you may have heard, square root of 2 is irrational, meaning square root of 2 is not a rational number, meaning square root of 2 is not equal to a over b for any integer. Oh, I forgot to close it. So you can never find a combination of one of these guys on top and one of these guys on bottom such that square root of 2 equals a over b for any a and b that are integers. Now, again, that's what they're being tricky, you know. Like you might think, oh, square root of 2 just equals square root of 2 over 1, and that is certainly true. However, if you look at the fine print, they're saying the rational numbers are only a, b, as long as the a and the b are integers. And if you write square root of 2 as square root of 2 over 1, while that might be mathematically true, and while 1 itself is an integer, square root of 2 is not an integer. I mean, we can get into why it's not, right? If you look at the calculator, square root of 2, you're going to get 1.4 something something something, which is clearly not any of these guys, because these guys don't have any decimal parts to them. Okay, so I just kind of told you that square root of 2 is not in the rationals, right? Well, basically any number, if you're any type of number that is irrational, you're irrational. Well, whether you're rational or irrational, here we have the set of real numbers. And again, basically, there's no other way to put it. All real numbers. I guess one way to put it is x values such that they're greater than infinity, than negative infinity, but less than positive infinity. Which is again maybe something that you've seen before. This is why you probably have seen sets, you just didn't know that they were called sets. An interval, negative infinity to infinity, is basically this, and this, as you can see, is a set. Right. So again, the only way to kind of say what a real number is basically if you have a line that reflects length. Let's just say length, right? And then suppose that 0 is right there, right? And then suppose that 1 is right here, right? So basically, 1/2 is going to be here, maybe, right? 1/3 is going to be there. 2 is here, right? So again, like I said, not every number is rational. We have irrational numbers too. So surprisingly enough, just because you can cut lengths into small pieces doesn't really mean that you'll get every single point in this line. Again, square root of 2 is going to fall somewhere here, right? So basically, yeah, I mean, I'm trying to make a big deal of something that just is this way. Any type of length that occupies a space in this line is just a real number. And let me just close it out with something that is, you could say, a number, but not a real number. Well, we have this thing called the complex numbers as well. Now, the complex numbers are the set of a plus bi, with the distinction that a and b are real numbers, and this letter I is not a real number, but it just so happens to have the ability that I squared equals -1. Well, actually, it doesn't really stop there. There actually is a bigger set than this. So in case you haven't noticed, the way that I'm writing this is, first you have the natural numbers, but as you can see, every single natural number is an integer, right? So if you're an element here, you're an element here, right? But then now, if you really wait a second, right? Any element here is also an element here. So for example, 3, right? You can write 3 as 3/1, and now this does satisfy the fine print of what a rational number is. I mean, -2 is just -2/1, right? Anything is anything over 1. So as you can see, if you're an integer, then you're also a rational number, right? If you're here, you're here. But if you're here, you're also here. And if you're a rational number, then of course you're a real number. The hidden thing is that one thing that you may have never noticed is that if you are a real number, then you are also a complex number. So I should have, maybe I didn't say that, right? This set is the set of all complex numbers. Complex numbers are any number that looks like a plus bi, as long as a, b, and real numbers, and I squared equals -1. And if you're still not seeing, okay, how is any real number a complex number? Well, for example, the reason why pi is a complex number is because pi equals pi plus 0 times I. So again, because 0 times, so just at this point you just have to believe that 0 times I equals 0, right? But the fact that I'm writing pi as pi plus 0i makes it so that now the fine print for what a complex number is works, right? Because pi is a real number and 0 is a real number. So yeah, pi equals pi plus 0i, right? So it is a plus bi in a way. And I chose pi, but there's nothing special about pi. You can do this with any real number, right? So as you can see, this is probably the weirdest thing that I've said so far, is that any real number is also a complex number. Yeah, I took way too long doing this, and I feel like I didn't really explain myself very well. So I would say, make sure to leave a comment on what I should explain more. I really don't want to. I'll come back to sets, or I'll come back to any idea that I presented in this piece of paper if you want me to, right? Like I said, even there's still a lot of ideas about sets that I haven't covered in this one piece of paper. But yeah, let's just leave it at that. If there's anything that you want more explanation about just the things that I covered in this one page, yeah, let me know. Put it down in the comments, and I'll try to do a better job. Like I said, I can't believe I spent basically more than half an hour just conveying what this piece of paper says. Alright, so we'll leave it there. And again, please comment. Give me some feedback. Goodbye.